Thank you, everyone. It's a great pleasure to be here, and I've followed the work from AO2 with a lot of interest over the last couple of years, so it's great to visit. So what I'm going to talk about today is the problem of generating and understanding visually grounded language. And so I'll be sort of picking on one example from each side of this problem. And the overall goal, I guess, that's interested me for quite a while in terms of vision and language is really about two things. So one is building AI systems that can communicate naturally with people. I think everyone here would agree that natural language is the ultimate API for dealing with a person. But secondly, we also need to understand visual context, because if we're trying to build systems that can be assistants and help, you really can't help if you don't know what's going on. So for example, one of the things that I think is quite motivating is trying to build systems for helping people with visual impairments. So for example, from the VisWiz data set, given an image and someone asking a question, please can you tell me what this item is? We'd like to be able to answer these types of questions. We're also very familiar with sort of personal voice assistants, but I think the visual context is very important here as well, because if we're cooking, following a recipe, for example, and we want some help, if the system doesn't know what's actually going on, then it's not going to be particularly helpful. And I guess really I think that there's not many computing systems that can't be improved with the addition of kind of these two goals, the visual understanding of context and the natural language. Even if you take the most boring thing you can imagine, which to me is kind of stock keeping and catalog systems, what if it sort of worked like this? A technician says, hey robot, what's the recommended spark plug gap for this model? The robot knows what this car is because it can see, so it can answer that question. Do we have the new bumper in stock? Well, not for this car because I can see that this is a metallic silver car. And so, having visual context, I think, is super important for all of these applications that we want to put a natural language interface on top of. So with that motivation, let's kind of delve into two different aspects of this problem. Firstly, in terms of generating visually grounded language, I'll talk a little bit about image captioning, and I think where I guess we're looking to advance that problem in a slightly new research direction. And then secondly, I'll look at understanding visually grounded language in the context of following instructions in an environment. So image captioning to me is pretty interesting because it's this fundamental problem of can you describe what you see in natural language. So given some input such as these two images here, we would like a system that can give a natural description of what's in these scenes, because this is really a fundamental building block of many other larger applications. So for example, a man and woman are riding an elephant in the river, or there's a large portion of pie on this platter. So one difficulty that's sort of plagued this research area is the problem of evaluation. So here we might have a candidate caption for this nice picture of a green car. And the way we typically evaluate is by comparing this candidate to a bunch of reference captions written by humans. And the most typical approach is that we convert all of these captions into their n-gram representation, and then we look for similarities between the two using some n-gram similarity score, such as cider, blue, meteor, or rouge. And so we see here that some of these n-grams are appearing in both, such as the green car. So we did some work in this area where instead of using an n-gram representation, we convert both these reference and candidate captions to a scene graph representation by parsing, which encodes the objects, attributes, and relations that are mentioned. And then we do a similarity score, which is called the SPICE metric, between the reference and candidate scene graphs. And so this was quite a neat approach, because we're actually examining whether the propositions that are encoded in the candidate caption are actually supported by the reference captions. And so we get a little bit closer to the kind of semantic content of the caption. And so this was currently the most effective caption evaluation metric in terms of correlation with human judgment. but there's still a bit of a problem here. Evaluation remains difficult, and so if we look at the progress on the COCO data set over 3 or 4 years now, there's been this tremendous progress, in this case looking at the CIDR metric, but it's slightly worrying that human performance on this metric is still down here. And so it's not entirely clear what this huge gain here represents in terms of, are we actually still attacking the sort of fundamental research problem that we wanted? Are the descriptions actually getting better? So let's just dive into a few examples and see if we can understand what's going on here. So I'll take as an example this model that we proposed a little while back, which has this sort of main idea of bottom-up and top-down attention, where we, instead of designing an attention system that took as input the spatial output of a CNN, which is what you see on the left-hand side, this is sort of some arbitrary grid of image regions across the whole image. We proposed a system that would first identify all the objects in the scene, as shown on the right-hand side, and then we can build a model that will attend to those objects and sort of combine all the attributes of those objects together. So this is a reasonable model to look at. It's no longer state-of-the-art, but it's near state-of-the-art, and it's sort of representative of current approaches because it's become a standard approach to image captioning and VQA. And if we look at the output of this model, this looks great. We've got 2 hot dogs on a tray with a drink, 2 elephants and a baby elephant walking together, a brown sheep standing in a field of grass, a man in a white shirt is playing baseball. Oh dear. Okay, so this is not baseball. Okay, but at least we've got the zebra laying down in the grass. Actually, there's a bit of a problem with the zebra. So one comment, I guess, is that these models can appear to do really, really well, but they also make catastrophic errors. And so if we were actually talking about using these systems in the world, for example, for people with visual impairments, this one in particular could be a really catastrophic error to make. So why do these ones work and these ones don't? And it really comes down to the training data. So if we look at the number of mentions of these visual concepts in the training data, we've got thousands of hot dogs, almost 10,000 elephants, 5,000 sheep, 14,000 mentions of baseball, but only 5 mentions of anything to do with karate, and 8,402 zebras, but only about 100 mentions of a tiger, which for these models in the context of the data set is virtually non-existent. So we have a bit of a data problem, you might say. If you look at this COCO training set, it's this very large data set of almost 600,000 captions, slightly fewer images because there's 5 captions per image. But all of this is built on top of about 91 object classes that were used to collect the images themselves, because COCO is fundamentally an object detection data set. And we can easily point out the images that we were looking at that worked, that come from this set, but what about everything else? Here we're sort of densely covering this very small selection of objects, but this isn't useful in terms of a model that we can then take and go out in the world. So there's this sort of need for a new research question around image captioning. The question when COCO was devised was, can we do this at all? Given enough data and a narrow enough range of concepts, can we describe these images and make it work at all? And I think the answer to that is now yes. And so the next research question here could possibly be, how do we learn the long tail of visual questions, visual concepts of things that are actually in the world that humans know about, so that we can then move this stuff from the lab out to the world and do something useful with it? So how do we scale to images in the wild? Now there's a fairly straightforward approach to this, where we might just collect more data. So given these images that were our failure cases, we can go and pay some people to write captions for these images that are better quality. But there's a lot of redundancy and duplicated effort here because we already know about men in white shirts. Our model already knows about animals laying down in the grass because we have zebras that do that and other examples. So a lot of what's actually missing is really the grounded nouns to learn about many, many more objects that are in the world. And of course the expense of doing this is prohibitive. I don't think anyone believes that we can really solve this problem just by paying people to annotate millions and millions of sort of visual concepts that we know. So an alternative idea is that we could at least start by exploiting existing data sources that we actually have, and in particular object detection data sets, because there's a couple of nice aspects to these data sets. One, they provide the sort of grounded nouns or objects that are probably the key part that's missing from our existing models. Secondly, they're orders of magnitude larger than COCO. So objects, open images, for example, I think has something like 7 or 9 million images, 600 categories, compared to COCO that has about 100,000 images and 80 categories. And also, these data sets can be scaled up in sort of semi-automatic ways, so it's a lot more scalable. The second thing that we can think about using is text corpora. If we're learning about a new object or a new concept like a tiger, there are text corpora that can provide us with sort of more knowledge about what's sort of linguistic and semantically appropriate ways to talk about a tiger. And so, motivated by this and sort of hoping to push image captioning towards the next research direction, we've proposed a benchmark to evaluate progress on this task. And so the setting is this. Given training data consisting of COCO captions data set, which contains 118,000 images, 80 classes, and full captions for each of these images, we combine this with the Open Images training set from Google, which is the object detection data set that contains, in the case of the bounding box annotations, about 2 million images. And what we would like to do is then build a model that can annotate images with captions for all of these new classes as well. So we're going to ask this model to describe images that contain concepts which it never saw a training caption to cover that concept. And so we've collected this validation and test set, which we call NoCaps, or the NoCap benchmark. And all of the images that will be used for validation and test come from the validation and test set of Open Images. And then we divide that into sort of 3 different subsets. So in-domain images are those which contain classes that are only found in COCO. So this is something that we expect existing models to perform well on. There's a sort of a near domain subset where we have some combination of some concept that the model should know very well, like a person or an umbrella. But we're also adding in new visual concepts here, like an accordion. And then there's the most difficult challenge of all, which is these images which contain classes that have really nothing at all similar to what's been learned in COCO. So for example, in Open Images, there's lots of sea creatures which are not present at all in COCO. And so producing captions for these that describe them accurately and fluently is a significant challenge. So NoCaps is short for, yes?
So this seems to suggest that the coverage of verbs, special prepositions, attributes is quite large, even in existing captioning datasets like MS COCO.
Yeah.
Which is why you're saying that all of that stuff I can learn from COCO. What I need to understand from Open Images is just the nouns. Have you done any analysis to sort of suggest that this is indeed the case?
So I'll probably qualify that a little bit. So I'm not suggesting that we only need the new nouns, but I do think it's the biggest missing part. So there is also a need to kind of learn new adjectives and new verbs and things. So for example, like dolphins swim. So a natural caption here might be something about dolphins swimming. it's not clear that that knowledge is present in Cocoa because it's a big leap to make from a Cocoa caption that talks about a person swimming to then talk about a dolphin swimming. So I do think there is a need for other things as well. But a lot of what's missing could come from these object detection data sets. In terms of the analysis, when we looked at, so after we collected this data set, we looked then at like how many new adjectives there are, how many new verbs, how many new nouns, and most of the new material is found in new nouns. I don't have those numbers to hand, but they're in the supplementary of the paper, which is can be found on the website. Now, partly that's self-fulfilling because we collected these captions based on an object detection data set, so it's not surprising that new objects, new nouns were primarily what we found. But that's at least partially answering the question, I hope. Okay, so this overall task that we're sort of focusing on isn't actually the first time this has come up. So I would like to point out this nice prior work and that this task has sort of appeared under the heading of novel object captioning. So there is about maybe 8 or 10 papers that have sort of built some community interest in this area. The main difference in terms of producing this new benchmark is that the previous work was evaluated on what was more or less a proof of concept data set where we took Cocoa, we held out 8 different object classes. They were selected to be very similar to some existing class. So, horse was in the classes that were seen with captions, and then zebra was considered a novel object, and the captions for the zebra were removed from the data set. The concern here is that, really this was a proof of concept with only 8 novel classes, and they're very similar. So we've expanded this now to over 400 novel classes and a much larger scale evaluation so that we can put more pressure on these models that have been proposed and sort of see are we really solving this problem or not. So from the learning perspective, the kind of key interest here, I guess, is 2 things. One is there are aspects of domain adaptation here. I mean, there are slight visual differences between open images and Cocoa, but primarily we're sort of looking at a transfer learning problem where we're trying to take information from these object detection data sets and improve our captioning models. Okay, so in terms of the actual validation test sets themselves, we selected a subset of all of the images in the open images validation and test set, and primarily we were interested in selecting those images that were most difficult and interesting from a captioning perspective. So we looked for even class representation and images that have multiple objects per image. And we ended up with something that's fairly similar to Cocoa. So we have about 4 object classes per image, which is a little bit more than Cocoa, and on average around 8 object instances. So you can have several instances from the same class, which is similar to Cocoa. So the visual complexity here is similar or a little bit more difficult than Cocoa, and then of course many more visual concepts. In terms of the collection interface, the sort of main thing to point out here is that this follows the Cocoa setup quite closely, with one difference, that we primed the workers here with the correct object classes. And we did that so that we could improve the quality of the collection of the captions that were collected. So it wasn't particularly a problem in this example, but in examples like this, we found that because we were now dealing with a much larger set of finer grained object classes, people just didn't know what they actually are. Does anyone know what this is? Red panda, very good. Okay, so an AMT worker would call this a brown rodent climbing up a tree in the woods. And so we would then just prime them with these object classes. There was an explicit instruction that they didn't need to use these classes, but they were there if they were trying to resolve some uncertainty about what they were looking at. And of course that comes with a concern that we might be restricting the linguistic variety that we might otherwise be collecting. So we did do a comparison to Cocoa where we sampled an equivalent number of captions from both data set, and we just looked at the number of sort of unique n-grams as some proxy of how much variety is there. So as we'd expect, we do still have more variety. Yes?
Was this also sampled within 80 object categories, or was it across tons of categories?
So this was across all of them. So yeah, we should also do across the same categories, I guess. Yeah.
Same number, yeah.
Yeah. Good point. We'll do that. Yeah. Because obviously we expect, we expect to have more, a larger vocabulary because of the existing words, and then that feeds into the others. So we should do that as well. So one question that comes up with the kind of benefit of proposing a new benchmark is, well, how many reference captions do we actually need? And this is something that no one's really thought about much, probably since COCO. Well, with the exception of 2 papers, so the CIDR and our work on SPICE, both papers kind of looked at this in terms of how many reference captions do we need, and it sort of seems like the sweet spot is around about 10. So for this benchmark, we collect 10 captions per image, which results in a data set all up of about 166,000 captions. So it's 10 reference captions per image, plus we collect another one as a human baseline. And so, yeah.
Could you explain why you came up with 10 based on this graph?
So I guess there's clearly diminishing returns. So for example, with CIDR, this is where people are evaluating on COCO with 5. There is a little bit more accuracy that can be gained, and our analysis with the SPICE metric and slightly different data set showed that depending on the metric, having a few more can help as well. But I think after 10, then the diminishing returns are very significant. So
Are these the curves for a human baseline?
So what these curves were for is this was a setup where there was a comparison of several captions to make a binary choice of which one is better. And the choice would basically be informed by each of these different metrics. So we would basically say whichever caption had the higher metric value, we would say was better. And then what we're looking at on the y-axis is what's the accuracy in making that selection. So basically what this is showing is that with 10 captions instead of 5, when you compare 2 different captions for the same image, your accuracy increases using these metrics to select which one is better.
But this isn't taking into account an important question, which is if you had more captions, then the score assigned to a novel human caption would also go up. And that's what you want. Because in a previous slide you said that with just 10 captions,
yeah,
the human baseline is recorded to be much lower, presumably because there's more diversity in the way humans write things.
So this is kind of going into the details, but from memory of these papers, what we're looking at here had a couple of different settings. So there was a setting where a model caption was compared to a human caption, and then there were settings that compared model captions from different models, and so there was a sort of whole mix of stuff that went into this, but I would have to check the papers to kind of get right into the details. Okay, so to kind of make this concrete, particularly we're having this discussion about how much variation there is. So when you see 10 captions for an image, you do see a lot of redundancy, but you also, by then you've really captured all of the different linguistic variation that is sort of reasonable, or at least close to all of it. And so this is an example from the near domain data set where the man here is from a known concept from COCO. The camel is the new thing, and the difficulty here is I guess introducing these new concepts. And then as an example of an out-of-domain image, here we have a tank and some military vehicles at a gas station. And so this is now getting very far from the realm of COCO and very challenging to build a captioning model that can describe this accurately. So let's get now onto the models that we use to approach this task. So the first one is the model I mentioned before, which we use as a baseline trained just on COCO. We then also consider a constrained beam search approach. So here what we do is combine our existing model with the output from a strong object detector trained on the OpenImages classes. So imagine we have an object detector that can detect some of the objects in this image. What we want to do is force the captioning model to mention those. So we encode these detected objects in a finite state machine so that we have an acceptor that would accept captions that mention those objects. So we can include plurals in here like tiger and tigers, and synonyms like maybe grass and vegetation mean the same thing. And so if we process a caption with this finite state machine, we only end up in the accepting class here if it mentions both of these concepts. And so in the approach, what we do is we use that finite state machine to force the captioning models to mention these things. So beam search is an approach that everyone's very familiar with to finding a high probability output sequence from a model like an RNN. So we use constrained beam search to basically take as an input not only the model but also this finite state machine, and then it will output a high probability caption that satisfies that finite state machine. And so this is some previous work we looked at EM&LP in this context, and I'll kind of leave, I guess, the details to the paper. But in terms of high level, we're basically able to force this model to satisfy these constraints, and we also incorporate a language model in order to deal with out-of-vocabulary words. And in the results that I'll show you, we use Elmo as that language model in the forward direction of Elmo. The second, yes?
So the captioning model, as per the NoCap setup, is trained on the MS COCO classes,
Yep.
right?
Yeah.
And so there's no reason for the captioning model to understand what a tiger is.
Yeah.
Well, in the tiger you had 100 examples, but some other thing you only had 5 examples.
Yeah. Yeah.
Unless the captioning model proposes tiger as one of the top n things, you're going to look at n sort of captions that are proposed,
Yeah.
or n concepts that are proposed, and then your constrained beam search is going to sort of encourage those concepts to be in your output caption.
Mhm.
If you've never seen what a tiger is, you can't
How does
expect
it
this
work?
to work, right?
So there's two aspects to this. One is, can it produce a good caption that mentions a tiger that's linguistically plausible? And the second is, can you do it at all? The can you do it at all is guaranteed by constrained beam search, that it will 100% produce a caption that satisfies these constraints. And the reason is that what you end up with is, in beam search, a separate beam for every state in the state machine. And in beam search, there's this sort of comparison step where you only keep the n best partial solutions at each step, and they compete with each other. But in this decoding algorithm, they only compete if they're in the same state. And so there's no competition between a caption that mentions tiger and one that doesn't. And so you can then basically guarantee in the end that if you take sequences from the state corresponding to the accepting state, they will satisfy the finite state machine, because in decoding they will have actually moved through all of those states. So happy to go through that in more detail offline. The second question, I guess, is how can it be linguistically plausible? You can force it to mention tiger, but it's never seen this word, so how can it work? So to solve that problem, we're basically using word embeddings. So in the initial work, we used GloVe and a dependency embedding, and these were fixed fixed at training time on COCO, and so then you could expand your vocabulary by just adding more rows into this matrix at the input and output of the RNN. And so in this work, we've become a little bit more sophisticated using Elmo, but the same concept is at work. Okay, so the other model that we look at is a model called Neural Baby Talk, which is a completely different approach as well. And this is work from Georgia Tech prior to my arrival. But the basic idea here is that we're going to produce a template where slots will be grounded in the image. And unlike sort of early work, there was a paper called Baby Talk, which is propose this type of method. The main idea here is that we can use a neural network to come up with this template and then still use the kind of idea of grounding these slots in the image and then filling these slots with the output of an object detector. Yes?
Your previous method, would that enforce all those 7 objects would have to be mentioned in the caption?
So that's a good question, and it's something that we've found to be quite important is, if you have a detector like this, how do you figure out which of these constraints you should enforce? And so we have some kind of heuristics that we used in the initial work, which are based on the highest confidence and the largest objects and things. But I think that's definitely an area for future work, because one of the problems that you expose with this type of task is how do you determine what's visually salient, what you should actually talk about? Because in the original COCO data set, you don't worry about that. You just have an end-to-end model and it just learns it from the data. But in these types of problems, we probably need to do more explicit modeling of things like that in order to have success. So yeah, it's a very good question. Okay, so the nice thing about Neural Baby Talk is that if we want to caption these novel objects, we can replace the object detector with one that knows about these new objects and hope to get reasonable results here as well. So that's the kind of setup. So big results table, but I'll try to just point out a couple of interesting things. So one, I guess, is, well, how hard is this task? If we take the first row, which is the model trained just on COCO, we can just pick out something like the CIDR score is about 56. Our best model, which includes constrained beam search and ELMO and sort of all our heuristics, goes from about 56 to 74 in terms of a CIDR score, and then the human baseline is about 87. So we can make substantial improvements over a naive model, but there's a very long way to go to get to a human standard. And one thing is this is kind of nice because we're not in the COCO paradigm where we're way above human and we don't know what that means. I mean, here it's fairly obvious that we can try to move in this direction, and it should actually mean we're improving on this task. The second thing is, do the language models help? Does ELMO help? The interesting finding here was that for anything that was sort of in domain or near domain, it didn't make much difference. Even if you have relatively few mentions of an object, it appears that the models on COCO were learning decent word embeddings. But for anything that's out of domain that you've literally never seen before, in that case, we were getting decent improvements from using ELMO. So I think there is sort of further to go in terms of how we might leverage text corpora and things to improve on this task. Incorporating ELMO is sort of the most obvious thing, but I think there's probably many other approaches. And finally, do better object detectors help? And the answer is yes, if we substitute ground truth detections. If we look at any particular result like CIDR, we get about a 10% improvement, or actually more than 10% improvement. So we will get some sort of tailwind from the object detection community. But even so, even with ground truth object detections, our models are not as good as human. So we can't just kind of sit back and say, well, let the object detection people solve this for us. We still need to figure out how we're actually going to use that information. And so to give some example, to put some sort of flesh on these bones, here's just an example of a few things that go right and a few things that go wrong. It's clear that the up-down model, which is the baseline model on COCO, it only knows about baseball. It doesn't know about dolphins and firearms. If you then add in some constraints, even using ELMO and things, you still get some weird things that can happen, like baseball rifles, or there are some problems that can occur with grounding. So we might have a marine mammal sitting on a dolphin because we don't have anything explicit here that says these things are actually being grounded to the same place in the image. And so, I think there's still a significant way to go. And I guess if you look at humans, as you'd expect, you have these very nice, accurate and reasonable captions. So in summary, we've proposed this benchmark. We're calling it a benchmark mainly because we aren't providing any additional training data. We're basically saying here you have COCO for captions, and here you have the largest object detection data set in open images. what can we do with the combination? And why not make aiming for models that capture the long tail as a kind of direction towards something that works in the wild, as the next research agenda for image captioning. And in terms of the kind of explicit results, we know that better object detectors and better language models will help. But to the kind of earlier question about that was really about saliency, there are all these other challenges in there about visual saliency, about determining what's the sort of entry-level category for some of these classes that we should mention, dealing with synonyms and grounding and not mentioning the same thing twice. And I think it gives us a reason to have a lot more structure in our models to sort of deal with some of these problems. So there is an archive paper, it's under review, and more information through this website, and we expect that the actual data and leaderboard should be available very soon, probably in the order of a week or so. Okay, so that was kind of part one. I'll go a little bit more quickly through the next part, which is somewhat, some is existing work, and then there's some work in progress that I think is really interesting that I'd like to talk about. So we're now looking at the other side, I guess, of this really big problem, how we understand visually grounded language. You may wonder why we chose to look at an instruction following task when there's sort of so many other interesting tasks. And I feel there's been this sort of interesting tipping point where the people that work on 3D reconstruction seem to have got to a point where this stuff works really, really well. And so now we're in a position where there's untrained users, taking cameras like this or even smaller ones and producing accurate 3D reconstructions of buildings that are now sort of in the millions. Even taking one company, for example, these guys have over 1 million 3D reconstructions of pretty good quality of large buildings. And so some of this stuff is now finding its way into the research domain. And to me, this is a very interesting time then to start looking at problems that are situated in buildings. And so many other people are also kind of coming to this conclusion, so that we're now looking at almost a new paradigm. I guess previously we had crowdsourced images and we put annotations on top of that like ImageNet, and we drove computer vision forward. So I feel that now there's an opportunity with sort of large amounts of raw data of 3D reconstruction to sort of put annotations on top of that and drive models that know much more about our human environments. And as well as the 3D reconstruction, of course, there's also other approaches using synthetic environments that give more control, and so that, obviously things like AI2 Thor and many others, and then many other tasks which are moving in this direction. And it's very exciting because most of this work has really been in the last year or so. But in our particular interest is in vision and language, and so we proposed this simulator based on the Matterport 3D data set. And so what we used was these panoramic images covering around 90 different buildings, and these are fairly densely sampled throughout these buildings, so that we were able to build a navigation graph that would link all of these panoramas at each point within a building. And we set this up as a simulator, so you basically have an agent that can kind of move along these navigation graph edges, and at each point they can then look around in any direction. So you have a nice outcome that you have sort of natural images with a lot of visual complexity, but we've sort of abstracted away some low-level details of continuous motion for the robot, which I guess was not our primary concern. And so on top of this, we built this data set for a problem called vision and language navigation, where given an instruction like this and a robot that's situated in this environment with the disks here representing the places that you could move to next, your task is to find this goal location. And so this data set was a reasonable size. We sampled about just over 7,000 sort of paths through this building, showed this to workers in Mechanical Turk to collect natural language navigation instructions, using a sort of immersive interface. And we ended up with this data set with an average instruction length of about 29 words. and an average trajectory of about 10 meters, which is something like 4 to 6 steps in the navigation graph. And so with an average vertex degree of 4 or so, then there's still quite a very large explosion of different trajectories that you could follow. So this is sort of what it looks like to move around. You can see that the agent is trying to follow some instruction, and they're hopping in between points as they move around, as they kind of move through this navigation graph. And in this case, I think they overshot, but then it's going to head back somewhere towards that couch in the window, which was the goal in this case. So it's been really exciting that this task has generated some interest in the community. So we put up this leaderboard, and we've had about 28 submissions, I think, in the last while, and some really interesting ideas are coming out. And so some of the things that are sort of driving progress here, one is pragmatic reasoning, having explicit models of the instruction generator, which not only used for data augmentation, but also to kind of reason about what's the most plausible route given the instruction. There's work that is focused much more on when we should stop in these sort of RL style environments and when we should backtrack. And there's some interesting recent work at NAACL using an idea they're calling environmental dropout, where we can basically mask out whole classes of objects in an environment as a way of kind of generating new environments and improving generalization. One possible concern, I guess, or not concern, but in terms of what's missing here, what has been found is that it's very important, as you'd imagine, to reason about alternative trajectories for this instruction. And so a lot of models are using search methods through the environment, like beam search, to sort of consider a whole bunch of alternatives and then figure out which is most likely. But that's not really conducive to robotics. If we're imagining, we have 40 different robots that are all sort of exploring simultaneously and then teleporting from place to place in order to reason about how to find the goal. So what we are interested in doing is reasoning about the trajectories in a map that we'll construct on the fly. So this idea is actually very nicely following from work at AI2, such as the interactive question answering paper. So the first part of this is that we will build this semantic map. So we've added depth to this Matterport simulator so that now we can run each image through a CNN, project that CNN down onto the ground plane, and then build this map using a GRU update so that as the robot moves around, we have this semantic spatial map. So that part is similar to previous work, such as mentioned at the bottom. There's other work like MapNet as well from CVPR last year. But the real question for us is, suppose we had this map, and let's suppose it was even the complete map to start with. Then we've got this quite complex instruction. How do we actually figure out where this goal is? This seems to be an area of still significant research interest. And so I might turn it over to you guys. Where do you think the goal is here in this map? I can help a little bit maybe by highlighting some of the things that you expect to see. So you're in a bathroom, you're going to leave, you'll see shelves, a sink, a stove and a sink.
It's on the middle right.
Yeah, that's sharp eyes, I think. So it is on the middle right. And the kind of intuition here for me that was interesting is that what's in this instruction is actually a sequence of expected observations in purple and a sequence of expected actions that you should take in green. And so if you have a map and you have a sequence of actions and observations, and you're trying to figure out where this agent ends up, then it actually starts to look a lot like a tracking problem. And so we've built a model for this that is actually a Bayes filter. And recently there was a few different works looking at sort of differentiable particle filters, differentiable other types of Bayes filters. And in our incarnation, it basically looks like this. We're going to take an instruction. We're going to decode it with a sequence-to-sequence model into a series of latent observations and actions. So these will just be vectors that, from the instruction, that represent what we think the observations and the actions might be, although that's obviously completely unsupervised. We then feed that into this Bayes filter that is going to have a histogram that represents our belief over where the agent is in the map. And we will do a prediction update with a motion model based on these latent actions about where we should propagate that belief in the next step. And then we will do an observation update in terms of what we think, given the map, represents, you know, a likely observation. And so then we iterate this over multiple steps to figure out where we think this goal is. And so this is quite a return to, I guess, more traditional approaches, but in a nice way that we can basically encode all of this in a neural network and train the whole thing end to end, you know, all the way back through the semantic map, the CNN, as much as we like. And so for the observation model, what we're using is a model called LinguiNet, which was proposed by the Cornell group in the context of an instruction following task. And basically, it's a sort of a UNet pixel-to-pixel architecture that also takes a language embedding as well, which we will feed from this sort of what we're calling the latent observation. And then in terms of the motion model, if we have a belief over the agent's position, then actually a motion model is very nicely implemented with a transposed convolution, because basically what this will do is take the belief in any bin of this histogram and propagate it to neighboring bins in the next step. And so this sort of has, you know, convolutions have this nice locality property, and so, you know, that's also something we want for a motion model. You know, we're not allowing the agent to jump from one side of the map to the other. They're going to make local movements at each step. And so to sort of show how this might work, given this instruction and this map, so here what the agent has is a map that was constructed by sort of running an agent around the area to get an almost complete map. And then here, this is after the first prediction update. So this is, we then have an observation, probability of the observation. We merge those to get a new belief. And then we continue with a motion update, so that sort of spreads out. We have a probability from the observation model. We merge those, and so on we go, propagating our belief through this map until we basically get to the goal. And so you can kind of see here, I guess, with these outputs from the observation model that this is all just learned from the text. So this is looking for things like stoves and sinks, etc., and considering that, you know, these areas are, you know, reasonably highly likely. And then the motion model here is actually still quite primitive. It doesn't even have the agent's heading, so it's sort of just blurring out to nearby areas. But so this we thought was a sort of very interesting idea, that we can start to take these algorithms and insert them in our models as sort of algorithmic priors that would then have nice properties. So we have geometry in terms of the projection model to create this map, and we have algorithmic priors in terms of having a motion model and an explicit observation model that give us this type of intuition and these results. And so in terms of kind of a larger experiment, what we've done here is run an experiment where we've got fixed trajectories, and in those trajectories the agent's moving 70% of the time towards the goal, and the other 30% of the time they're moving randomly. And so you can see over those movement time steps, the area of the map that the agent has is sort of larger. The goal is often not visible at the beginning, so as the agent moves further, by the fifth time step, around 67% of the time you can see the goal. So we're still trying to predict this goal before it's even in the map. And we compare to a couple of different approaches. The first one is a hard-coded approach where we want to exploit the characteristics of the data set. So we basically figure out what's the average length of distance to the goal. We kind of draw a radius at that range, and then we pick the area that has the most map in that, most observed part of the map in that area, because we know that on average the agent's heading towards the goal. And so this kind of hand-coded exploit can get a certain number. If we use the LinguiNet model, consistent with the Cornell work, to just globally predict where we think the goal is, it will do substantially better. But if we use our filtering approach, which includes the explicit motion model as well as the observation updates from LinguiNet, then we do substantially better still. So this is sort of quite exciting to us, that you can actually treat a natural language instruction as a sequence of observations and actions and drive a differentiable Bayes filter from there. And so where we're sort of headed with this, yeah.
So why would I expect, if the goal is unseen, to be able to guess where the goal is?
So it's basically because you're going to get like a sort of partial trajectory with some things that you'll see along the way. So for example, if I said to you, go out the door, out this side door over here, and wait on the other side of the hallway. Even though from here I can't see the hallway, I could still have a fairly good prediction in a map of where that should be. Because it's relative, it's I guess not far away from something that you do know or you can observe. And you may still have some parts of the sort of action space, I guess, like go straight across the hallway, that would sort of give you some information as well.
That you could just traverse on the map.
Yeah. So because we're training this in maps that are partially observed, it still makes predictions about holes in the map as well. So just to be kind of completely clear about this, what we're doing here is not figuring out where the agent is. So in this setting, we actually know where our agent is all the time, but we're interested in this problem of, given the instruction, where is the goal? And so our approach to that is to kind of co-opt this traditional robotics approach and say we're going to do a tracking approach to figure out where the human demonstrator would have gone. And so in our complete model, this is a sort of subpart that which we will run at each time step. So every time the map gets updated, we rerun the filter to update our prediction or our belief of where we think the goal is, given the full size of the map that we have. And then, of course, there's a remaining part to this, which is we need an actual policy to move our real agent around using this belief as the kind of main input. So I warned you this is work in progress. This is where we're at. We're kind of excited about this, and I wanted to talk about it because I'm interested in hearing what people think. But we haven't yet got our full results on the VLN leaderboard. But we're kind of excited because we're, I guess, incorporating geometry, similar to the previous work from AI2, but now we're also trying to incorporate these algorithmic priors. And the important outcome of this is that this is now conducive with robotics, because we're no longer reasoning by moving through the actual environment, but we're reasoning in the map. So very finally, I guess I've got maybe, well, depending on how much time for questions, not much time. Have we finished this goal of communicating with agents naturally and understanding visual context? No, we haven't. A couple of things that I think are interesting directions from here. We have this setting where we imagine some use cases, we manufacture data, we build a model, and then we deploy it to people. There's a problem here, I guess, that if we're deploying conversational agents, most of the data they experience will be after we've actually put them out in the world. And so, there are approaches where people want to try to continue to learn from this and maybe do lifelong learning or some other approach. Possibly a bigger problem, if we start thinking about agents that are situated, that are using visual context, is that every user and every situation is different and stable. And so that's a very different paradigm from the kind of train deploy paradigm that we often think about, because there's sort of no single target domain. We've got these heterogeneous target domains. And how we're going to approach that, one thing I'm kind of interested in, I guess, that doesn't seem like a research direction that gets a lot of attention, is giving users the ability to actually personalize and fix the agents that they're dealing with, rather than assuming that we can do that through the agent on its own. Rather than sort of lifelong learning, saying that the agent is just going to learn from its experiences. I kind of feel that we should be thinking more in the context of a teacher and giving that teacher, the user, the ability to actually make improvements to the agent through a natural language interface or something similar. And users are smart and creative. I mean, you look at the things that people do in online worlds and hacking equipment, in building game mods. So to me, this seems an interesting direction. And I think the other thing that's of great interest is cooperative dialogue training. We have this continued sort of series of findings that in computer vision, data augmentation is essential to sort of do anything. In machine translation, back translation works really well. In RL, self-play against other agents is the key. But how do we make these types of models work for cooperative language models? How do we train models where you have one agent talking to another without having these models drift away from natural language? This seems like a very hard problem, but a very promising one. And incorporating structure in these models, what you might call algorithmic priors and visual grounding and things, I think to me seems an interesting way of pushing in that direction. So I'll stop here. Thank you very much for hosting me. I'd like to just acknowledge some of the people, which is primarily here the people involved in the NOCAP's work and also in the more recent work on vision and language navigation. And I hope, given that I've used up pretty much all the time, I hope everyone had a chance to ask questions during it, which I think you did. So thank you very much.